today's talk in this European seminar. And it's a real pleasure to introduce our speaker today, who is Victor Hildebrandsson from Linköping University. And he will speak, as you can see, on Octonion algebras over schemes and the equivalence of isotopes and isometric forms. So, Victor, whenever you like.
Thank you so much, Alberto. Perfect pronunciation.
Thank you.
And hello, everybody. Thank you for having me here. As Alberto said, I will talk about Octonion algebras over schemes. And the work I will present is in a large part my master thesis, which was supervised by Seidon. So I'm glad that he's here, and I'm glad that my current supervisor is here as well, Joachim. Yes, so let's see. Yeah, perfect. So the outline of the talk will be a short introduction about the motivation and the goal for the thesis. Then I will talk a bit about the definitions we will use from Octonion algebras over rings, and then their generalizations over schemes. We will discuss, or define rather, the twistor Octonion algebra and show that it is isomorphic to isotopes of the Octonion algebra. And then lastly, we will show the equivalence of isotopes and isometrics. So Octonion algebras are composition algebras of rank 8. And such algebras come with a norm. And I don't remember when, but in the 50s, van der Vlieg and Springer showed that over fields, Octonion algebras are completely determined by the norm in the way that two algebras are isomorphic if and only if their norms are isometric. However, it was shown by Gille, Philip Gille, that over rings, this is not the case. And in 2019, Seidon and Philip found a construction of these non-isometric octonions with isometric. It's wrong here. It's supposed to be isomorphic. Thank you. Non-isomorphic Octonion algebras, but with isometric norms. And it's the theorem shown here that two Octonion algebras have isometric norms if and only if one is isomorphic to an isotope, which we will define later. And in the 90s, Holger Peterson defined composition algebras over a general locally ringed space. And then the question that was asked by Seidon to me was to consider if this construction that he and Gille proved, if it generalizes to Octonion algebras over schemes, since Octonion algebras over rings by the usual equivalence of rings and affine schemes. So an Octonion algebra over a ring can be considered an Octonion algebra over an affine scheme. And then the construction should generalize, but will it also generalize to non-affine schemes? So Octonion algebras over a ring. So we let R be a unital, associative, commutative ring. And throughout, we will assume that our algebras are unital. Then an Octonion algebra is a non-associative R algebra C, which is finitely generated projective of rank 8 as a module, and which is endowed with a regular multiplicative form Q. And for those of you who maybe have not seen that many Octonion algebras before, the rank of a module, of a projective module at some at some prime ideal is the rank of the free localized module. And we then and the definition is that we demand that this rank is 8 for all prime ideals. And a quadratic form is a map satisfying this condition. And these two conditions, I should rather say, that the elements of R will be squared when taken out of the form, and this B form should be bilinear. And it is multiplicative if it satisfies this multiplicative condition, and regular if this induced morphism isn't isomorphism. I should have said in the beginning, but please, if anybody has any questions, just interrupt me. So an example of an Octonion algebra is the Zorn algebra, which is the set of matrices with elements of R in the diagonal and 3 vectors of R in the skew diagonal, with this multiplication here, where these UTV are just scalar multiplication, yes, scalar products. Scalar products, sorry. And these U times V are the vector products defined in the usual way we do in linear algebra. And if we use the determinant as the quadratic form, then the Zorn algebra will become an algebra over our ring R. And this works for any ring R. So if we have an Octonion algebra and we have some invertible elements A and B, then a principal isotope of C is the algebra with the same underlying module, but with this new AB multiplication. And we will denote this isotope by CAB. And yes, and then we have the Octonion sphere, which is a group scheme sending any, so here S is some R algebra, and this scheme sends this S to the set of the extended scalars over this Octonion algebra with a norm of 1. And then the theorem of Seidon and Philip is that 2 Octonion algebras have quadratic forms which are isometric if and only if there exists some AB with norm 1 such that this C prime Octonion algebra is some isotope, is isomorphic to an isotope of the other one. So we can see it as a twist, as these Octonion algebras are twists of each other. Yes, then we come to Octonion algebras over schemes. So, yes, so an Octonion algebra over some scheme X is a tuple, CQ, where C is a sheaf of algebras, such that for every affine set U, the underlying module of this C is finally generated, it's supposed to say, projective and of constant rank 8. And this Q is a morphism of sheaves, such that for all affine open sets U, QU is multiplicative, regular, and quadratic. Is a multiplicative, regular, quadratic form of this CU algebra. And again, in this setting, we call Q the quadratic form of C. And yes, so if we have, if X is an affine scheme, then this definition gives us back the exact definition we just gave of octonion algebras over rings, and using this usual categorical equivalence, we can also go the other way around. So octonion algebras over a ring are exactly the same as octonion algebras over an affine scheme. So yes, so this quadratic form induces two other maps: the bilinear form, which is exactly the bilinear form we saw earlier, and a natural involution, which can also, of course, be done in the ring case. And these are the definitions. And we also, maybe unclear notation here, but this thing down here is what I want to say there is that this bilinear form we have here is exactly the same as each bilinear form that these octonion algebras have. And then another construction. So similar to this pullback construction with the forget the name now, but these extension of scalars that we have for algebras over a ring, we want to have some pullback for our algebras. So in the ring case, this pullback becomes again an octonion algebra, but over the new ring S, or the R algebra S, and we want some pullback that pulls our octonion algebra from being over X to being over some X scheme. So we take an octonion algebra over X and let Y be some X scheme. Then we have this pre-shift where this F inverse C and F inverse OX are inverse image sheaves. And this thing will unfortunately only be a pre-sheaf, so we have to take its sheafification, its associated sheaf, and we let this be our CY. And then this CY will also be an octonion algebra. I notice now that I hope it was written here, yes, that this definition was done by Peterson in the 90s. Yes, he should have his due credit. And also that this pullback construction is well defined and becomes an octonion algebra is also a result by him. Yes, and we'll need this for later. So if we have some global section in our octonion algebra over X, then these AY, which is just this equivalence classes in this set, tensored with the identity here, will become a global section over this new algebra, this pullback algebra. And yes, so an example, the important part of this example is that we can construct by this pullback a octonion algebra over any scheme. So any scheme has an octonion algebra over it. And this is because, as we said before, we can define the Zorn algebra over any ring. and hence over any affine scheme. So we define the Zorn algebra over the integers. And then, since every scheme is a scheme over the integers, which follows from the fact that any ring is a algebra over the integers, and then any scheme is made up of affine schemes. Then it follows that we can make this pullback from this Zorn algebra over the affine space till an Octonion algebra over our scheme Y. I think that Peterson also have defined the a Zorn algebra, I should say, over these over a general locally ring space. And I unfortunately have not checked if these will become exactly the same, but I would not be surprised if they are. But I won't say more than that. Yeah, and then we can construct the Octonion unit sphere once again, but over a general X scheme, and it follows exactly the same procedure as the Octonion sphere over the rings. It sends a scheme to the set of global sections with norm 1. And then an isotope of an Octonion algebra for some pair AB with section with the norm 1, as I said, some global sections with norm 1 over our Octonion algebra. An isotope of this AB is the new chief of algebras, such that for any open set we have this new Octonion algebra, which similarly to the ring case is the same underlying module as this C, but with this new multiplication where we multiply some elements in the algebra, first with the restriction of A and the restriction of B, and then together. And this will again be an Octonion algebra. Are there any questions so far? Okay. Then we will construct the twisted Octonion algebra, and from now on we will assume X to be some scheme, and we will denote the X scheme Y by just its base scheme. And we let C and Q be some Octonion algebra over X. Then we can define the group scheme RTC by sending any X scheme Y to this long set of triples satisfying this long equation. And recall that these kappas are the natural involution that we had here. Yes. And yeah, these triples are elements in elements in the special orthogonal group scheme. And in fact, this group scheme RTC is a closed subscheme, so we can just multiply all our elements component-wise. And this scheme will act on this pair of Octonion spheres by this action for any y scheme, x scheme y. And this action will induce the map that we call pi, sending these triples to this action on the unit, the Octonion unit, yes, which will always have norm 1. So it is an element in the Octonion sphere. Then the Octonion, no, the automorphism group scheme is defined as just the automorphisms of our Octonion algebra, and we'll let this stab be the stabilizer, or I have been told that it also may be called the centralizer of this group action that we have here in this point. So it's the set of triples which act on this point 1, 1 and gives us again the point 1, 1, or the element 1 rather. And then we have our first theorem, that the first part is that the stabilizer is exactly the automorphism group or the inclusion of the automorphism group in our group scheme. But we will, except from this theorem, not think of this, or just note this by the automorphism group. And then part 2, that we have that the quotient sheaf that we take by quotienting our scheme by this inclusion of the automorphism scheme is a representable scheme, and the map induced, so induced by this pi here, is an isomorphism. And the first part follows, the first part follows more or less directly from the affine case, which was shown by Seidon and Philippe. And for the second parts, we have that this automorphism group is smooth and hence flat, and it is also of locally finite presentation. And then we have a theorem in SGA that this quotient is representable, and that our induced morphism is a monomorphism. And then we have to show that so what we then want to show is that restricting this morphism, we come to the affine case, which again is proved by Seidon and Philippe. So what we have to then show is that the restriction of this whole thing, of this quotient, is again the quotient of the restrictions. I think I said it in the right order. And this follows from the universal property of sheafification. And then it follows again from the affine case. So I have not written it here, but UIs, the UIs are affine subsets of, no, affine subscheme, affine open affine schemes of our scheme X. Yes, any questions? Yes, and from this theorem, it follows that the inverse of this pi is an torsor over our automorphism group scheme, or it is an automorphism group scheme torsor over our pair of Octonion spheres, rather, in the FPPF topology. And yes, so we denote our automorphism scheme by G. We will do this throughout, but we will also denote it by out C. So I will go a bit back and forth if I remember correctly. Then we define the pre-sheaf of X schemes, EAB, by this Cartesian product and quotient, where two elements are similar if there is some automorphism such that they such that we have this equality. And then will it EAB wedge GWC, a mouthful, be the sheafification, and this is then the twisted Octonion algebra. And we have a linear structure on EAB, which is induced by these three conditions. So we have these addition, multiplication, and scalar multiplication. And together with the quadratic form defined by this, which will be well defined since this it will be invariant of this T chosen by this T. Then this EAB will become an Octonion algebra over OYY. And then we can define this algebra map, algebra morphism. And in our next theorem states that this algebra morphism will induce a map which is a natural isomorphism of sheaves of algebras. Yes, so from the universal property of sheafification and the fact that we have a torsor of an automorphism group torsor, it will be enough to check the isomorphism claim of this map omega. So we only have to check that this is an isomorphism, and it suffices to check X schemes Y such that this pi inverse is non-empty. And the fact that it's the universal property of sheafification that makes it enough to check this algebra morphism, and it's the G torsor part that makes it sufficient to check only schemes such that this is non-empty. And then it's just a straightforward calculation showing that this is an isomorphism. And for naturality, it follows from the affine case, since naturality is a local property. Yes, so here G is not the automorphism group. So here is G is just some sheaf of groups, and for some sheaf of groups, we denote the isomorphism classes of G torsors by this first cohomology. I think yes. And then we define these sets S1 and S2 to be the kernel. So these first cohomologies, or here, these first cohomologies will be pointed sets, and then we have a well-defined kernel. So we can define these S1 and S2. And they will all, for our group schemes, G, RTC, and this O is it's the orthogonal group scheme, and they will all have the same base point, which will be our Octonion algebra. And then the claim is that these two sets coincide. And the first inclusion is follows that the inclusion of the automorphism group into the orthogonal group factors through our inclusion of the automorphisms into our group scheme RTC, and hence the kernel of this of the induced map, the map that this induces over this first cohomology, will be in S2, and that kernel is exactly the set S1. And for the other inclusion, we have, by a result of Gille, this bijection, where this whole thing is the set of orbits of this action by and yes, so this action, if we then take some isomorphism class in S2, we take some x in this set. Yeah, the set of orbits is in bijection with the elements of our Octonion pair of Octonion spheres. So we take some x such that phi of x maps to our isomorphism class. Then we find that this x lifts to some pair AB of norm 1, such that we have these isomorphisms, or this is the isomorphism we proved earlier, and the pair AB induces lifts to this isomorphism. And we saw earlier, I believe here, that this W scheme maps this our Octonion algebras Y, or maps a scheme Y to our Octonion algebras, and since they are here naturally isomorphic, we get that this Octonion algebra is isomorphic to this Octonion algebra, and hence are in the same isomorphism class. And then and then we have that C prime must also be in 1, since this will be in our set S1. the corollary to this is exactly our claim that two Octonion algebras over a scheme X have isometric quadratic forms if and only if there exist some global sections of norm 1 such that C prime is isomorphic to this this isotope CAB. So again, by the same result of Gille, this S1 that we have here is exactly the set of orbits that this of the RTC action on our pair of Octonion spheres. And this set of orbits will be as a set in bijection with our quotient here, since this is the group quotiented with its stabilizer. And we also showed that these we showed this isomorphism. And we also showed that the twisted Octonion algebra is isomorphic to an isotope of the Octonion algebra. So again, we have in bijection we have a bijection to the isomorphism classes of our Octonion of our isotopes of our Octonion. So S1 classifies all the Octonion algebras which are isomorphic to some isotope, which are the same isomorphism class as some isotope. And we have the bijections that the first cohomology of our automorphism group is exactly the isomorphism classes of Octonion algebras over X, which are locally isomorphic to our base Octonion algebra. And the first cohomology of our orthogonal group scheme is exactly the isomorphism class of a module sheaf with some quadratic form, which is locally isometric to our Octonion algebra norm. And then this set S2 is exactly the Octonion algebras which are sent to the base point, which is our base Octonion algebra. So we have that this set is exactly the set of the isomorphism classes of Octonion algebras which have quadratic forms isometric to the isometric form of our base Octonion algebra. And so the set S2 classifies Octonion algebras whose norm is isometric to our base Octonion algebra norm. And by the equality of our theorem before, we have the statement, which I can show again. Yes, so I will finish off, maybe a bit early, I see, but anyways, by talking a bit mentioning what this result can be useful for. So we talked in the beginning. I mentioned that over fields, Octonion algebras are completely determined by their norm, and this result that we have given here can change this question if an Octonion algebra over some specific scheme is completely determined by its norm. So we find an equivalent question, which is that here on the left-hand side, we have the statement that an Octonion algebra is completely determined by its norm. And this will be then, since this part is equivalent to the statement that this C prime is isomorphic to some isotope of C, then we must have that C is isomorphic to all its isotopes. So instead of trying to show that it's that an Octonion algebra is completely determined by its norm, we can instead examine is the best word, Mary, if all its isotopes are isomorphic to the base, or all its isotopes are isomorphic to the main Octonion algebra. And when this could be interesting is when looking at local rings. So Octonion algebras over local rings are another example when octonions are completely determined by their norms. And this then gives us a framework to explore whether or not this is true for Octonion algebras over the punctured spectrum of local rings.
What is this punctured spectrum?
So it's the spectrum of the local ring, and then you take away the maximal, the only maximal
Okay.
ideal. Yes, and so thank you.
Thank you. So many thanks for this beautiful talk. And well, there is time for questions or comments. So please go ahead. Actually, it was some points. Well, this is difficult for me. I'm not much familiar with all the techniques using torsors and so on, but I wonder whether really what you prove is that if you have two Octonion algebras over the schemes which are whose quadratic forms are isometric, what you have is that locally one is isomorphic to a twisted Octonion algebra over the other, but in principle only local on open affine subsets. And then what you prove is that this can be done globally, right? Is this?
Yeah, exactly.
This is,
yeah, exactly. So if I remember correctly, they should be locally isomorphic from the beginning, and so this shows that so the isotopes should be locally isomorphic to its non-isotope, I suppose. But here we show that
you can take A and B global sections.
Yes. Yeah, exactly.
Yes, which is, I believe it is amazing. But of course, the techniques are quite difficult, and so anyway, the schemes RT that you use are what correspond to the spin group related to the Octonion in the classical case, right?
Exactly. So I never really show it or consider the spin group directly for myself, but in Seidon and Philippe show in their paper that that their version of this their affine version, I suppose, of this RT scheme is exactly the classical spin group.
Yeah, but even over fields, it's quite convenient to think of the spin group attached to an Octonion as related triples of orthogonal transformation. So
Yeah,
even in the classical case, this is quite interesting. So yeah. Okay, thank you very much. Any question or comment that you may want to make to? So there is a question in the chat. So it says, so we can use algebraic geometry language. Why is this effective? This is the question. Why is the algebraic geometry language effective?
That is a good question. Yeah, I'm not really sure. So I will just think out loud here, but these algebraic techniques, the things I mainly used are these torsors, which for one example made this theorem easier, because then we like this torsion, this G torsor part made it so that we can only look at y, schemes Y, such that this thing holds, which was exactly what we needed, which is exactly what's needed to show that this map is surjective. But that's more just an example, and this whole picture I'm not sure, unfortunately. I have just used it and not thought about why.
Well, I guess that if one uses algebras over schemes, one has to use.
Yeah. Of course, that's the.
But I guess that even if one is dealing just with algebras over rings, probably one is forced to use algebraic geometry and not just rings. I mean, so.
Yes,
Yeah.
of course, the paper by Seidon and Philippe uses schemes quite a lot.
If I may add to what you said, Victor, it's exactly what you said there. From another point of view, this theorem that you're showing right now, it's somehow, with algebraic geometry, we know that the left-hand side is what really gives us all isotopes. I mean, we can construct the isotopes algebraically, but there is no way to know that we've got everything unless we use algebraic geometry. So the theorem you showed with S1 equals S2, I'm not sure if there is any, I mean, to my knowledge, there is no other way to show such a thing except using torsors and algebraic geometry. So
Okay, any other comment? Well, this is not the case. Let's thank the speaker again for the beautiful talk.
Thank you.
And I guess we will resume next week with another talk, which I'm not aware of the title or whatever. So, but see you next Monday. So, bye everyone.
Bye.